once again welcoming you all to second lecture of week 11. In last lecture, we discussed about design of different kind of digital to analog converters. In this lecture, we shall be starting our discussion on design of different types of analog to digital converter. Means here we shall understand how giving an analog input provides equivalent digital output. So, an analog to digital converter, as I have said, takes an analog input voltage A, and this analog voltage can be some physical variable like temperature, pressure or any continuously changing signal. This signal is sensed using transducer to produce an equivalent analog output voltage A. When this analog voltage is given to an analog to digital converter, we get an n bit digital output from D0 to Dn-1. This digital output produced is proportional to analog input. But there is an issue with analog to digital converter. We all have known that in a DAC, input is digital in nature and we can keep the digital input constant during conversion period. But analog voltage changes continuously, and during analog to digital conversion process, change in analog voltage can cause error in output. Due to this problem, analog to digital conversion is done in two stages. Have a look at schematic diagram. Here, first stage is sample and hold circuit, to which analog input is given. This circuit takes analog voltage at particular instant of time and holds that voltage for some time. This way we can get constant voltage during conversion period. And second stage is ADC block, which performs quantization and encoding of sampled signal and provides binary code at the output, which we shall discuss in detail in coming slides. Sample and hold circuit and quantization process you have already learned in previous weeks of this course. That is why we will go through it briefly. So, let us see how a sample and hold circuit works. The sample and hold circuit consists of some buffers, capacitors and electronic switch as shown in circuit diagram. When switch is turned on, the capacitor gets charged by input analog voltage. The time during which capacitor is charged is known as sampling time. When switch is turned off, the capacitor holds that sampled voltage to provide constant input to ADC. This time is known as hold time. Control signal is used to turn on and turn off the switch. This way sample and hold circuit works. Now the question arises, at what interval sampling should be done? So to answer this question, let us go through Nyquist theorem. Nyquist theorem states that a band limited analog signal, band limited means signal contains many frequency components, but those frequencies lies in the range of f maximum to f minimum. So a band limited analog signal that has been sampled can be perfectly reconstructed from an infinite sequence of samples, means sufficiently large number of samples. If the sampling rate is more than twice of f maximum, then if the sampling rate is more than twice of f maximum sample per seconds, where f max is highest frequency in the original signal. So, if we have a band limited signal with maximum frequency component of 1000 Hz, then for perfectly reconstructing the signal, sampling rate should be more than 2000 samples per second. Now, if sampling frequency is less than twice of f maximum, then there will be an aliasing error. So, what is aliasing error? Aliasing is when the digital signal appears to have a different frequency than the original analog signal. So, this was all about Nyquist theorem, and we can say increasing sampling rate increases accuracy of conversion. Let us have some example for better understanding of sampling and Nyquist theorem. In these examples, for better understanding, we have taken signals with single frequency component. Look at first waveform. We have a sine wave with frequency 1 Hz and red dots shows sampled signal which are sampled at 10 Hz frequency, which is 10 times of original signal. So, if we do not have original waveform, by joining the red dots or by joining the sampled signal, we get almost same signal. Now, look at second waveform. Here we have taken a sine wave with frequency 5 Hz and samples we have taken at the rate of 10 Hz. So, sampling frequency is exactly twice of original signal frequency. Now, if we remove the original signal and just by joining the sample values, we get a horizontal straight line. It means we lost the information that our original waveform was a sine wave. So, this happened because we are sampling at a frequency exactly twice of f maximum and we are not sampling at a frequency more than twice of f maximum. So, now let us see the bottommost waveform. Here we have taken a sine wave of frequency 8 Hz and sampling rate is equal to 10 Hz. Means sampling frequency is less than twice of f maximum. In this case, when we remove the original waveform and reconstruct the waveform using red dots, we get a signal which also looks like a sine wave, but it has entirely different frequency. This is called aliasing error. Now, let us understand second stage of analog to digital conversion. In this stage, sampled signal is fed to a block where quantization and encoding of sampled signal is performed. Quantization is a process of assigning value to a sampled signal from the discrete set of values. Quantization introduces error in ADC output known as quantization error. For example, if we have 3-bit ADC and range of ADC is 0 to 8 volt, then after quantization we will get 2 to the power 3, that is 8 discrete levels. These levels will be 0 volt, 1 volt, 2 volt and so on up to 8 volt. If the value of sampled signal is less than 1 volt, then after quantization it will be assigned value 0 0 0, and for sampled signal between 1 volt to 2 volt, the value will be assigned 0 0 1. So, the signal between 1 volt to 2 volt, that is if we have a signal of 1.5 volt say, that will be also assigned the value 0 0 1, and a signal with value 1.2 volt, that will also be assigned level 0 0 1. So, this causes error and this error is quantization error. Resolution of ADC decides how close quantization value is to actual value. After quantization, encoding is done. Encoding is a process in which a unique binary code is assigned to each quantized level. Let us talk about resolution of ADC. In DAC, step height was a measure of resolution. Now, in ADC, change in analog input voltage required to cause 1 bit change in digital output is resolution. In ADC, digital output changes in steps. So, to change digital output by one step, minimum change that should be done in input is resolution. So, least significant bit LSB of ADC gives resolution, which you can understand in the coming slide. Suppose we have a linear n bit ADC, then in terms of voltage resolution or LSB will be equal to FSR by 2 to the power n. Here FSR is full scale voltage range and its value is V maximum minus V minimum of the input voltage. In terms of number of bits, resolution will be equal to n, and in terms of percentage, resolution will be equal to 1 by 2 to the power n into 100. Now let us see some examples. Suppose we have a linear ADC with 8 volt full scale input. If n is equal to 3, then resolution will be equal to 8 divided by 2 to the power 3, which is equal to 1 volt. Now if the value of n is equal to 4, in this case resolution is equal to 8 by 2 to the power 4, which is equal to 0.5 volt. So for larger value of n, resolution is better. Also we can improve resolution by reducing full scale range without changing the value of n. Let us understand with an example. We have a 3-bit ADC with full scale range of 8 volt. This will give resolution 8 by 2 to the power 3, that is 1 volt. Now if we change the full scale range to 4 volt, then the resolution will become 4 by 2 to the power 3, that is 0.5 volt. So we can improve resolution by changing value of FSR also. Now here we have drawn a graph between digital output and analog input for a 3-bit ADC having full scale range of 8 volt. This graph is transfer function characteristic of ADC. So for an infinite resolution, transfer function characteristic of ADC is a straight line. It is shown here with the help of a blue line. Practical transfer function characteristic looks like a staircase as shown in the diagram. So everything we have learned yet about quantization and resolution can be understood through this characteristic. For 3-bit ADC, there is total 8 states after quantization, which we can see on the vertical axis. Minimum detectable voltage or resolution is equal to 8 by 2 to the power 3 for a 3-bit ADC, which is equals to 1 volt, and which is also equals to LSB. This you can see in the characteristic that 1 LSB is equal to 1 volt. Now if the sample input value is changed from 1 volt to 1.5 volt, the digital output will remain same, that is 001. This error is due to quantization. This also you can observe in the diagram. So maximum quantization error that can occur is 1 volt for a value of 1.1 volt and for a value of 2 volt. For both the values we get same output 001, or in general we can say it is equal to 1 LSB, which is true for all number of bits. I have repeated all the examples here so that we can analyze it through the characteristic. So for better resolution, quantization error is reduced. Now let us understand about different designs of ADC. We shall be discussing about different designs of ADC in the coming slides. The first type which we are going to discuss is flash type ADC. This ADC is known as fastest type of analog to digital converter, but problem is that it requires too much hardware. Let us see how. So flash type ADC is also known as parallel ADC because conversion of n bit digital signal occurs simultaneously rather than sequentially. Due to this reason, it provides fastest conversion among all converters. Suppose we have n bit ADC of flash type, then we need 2 to the power n minus 1 comparator, 2 to the power n registers, and 1 2 to the power n minus 1 bit priority encoder. So here the main drawback with this kind of ADC is that it requires large number of hardwares. Let us understand the design of flash type ADC. Here we have used comparators, and these are analog comparators, and these comparators take two different voltages at positive and negative terminal, and it provides digital output if positive terminal voltage is greater than negative terminal voltage, then digital output is high, but if positive terminal voltage is less than negative terminal voltage, then the output is low. Let us see the design of 3-bit flash type ADC. Here we need 2 to the power 3 minus 1, that is 7 comparators, 2 to the power 3, that is 8 registers, and we need one parity encoder with 2 to the power 3 minus 1, that is 7 inputs and 3 outputs. Now let us see how does it works. So here we have 8 resistances of value R and voltage applied at point A is Vref. Let us calculate voltage across all points from point B to point H. Since here all resistances are connected in series and last resistance is connected to ground. Also, all resistances are equal in magnitude, therefore, equal voltage drop occurs across each resistor. So, voltage between point H and ground is Vref by 8 because 7 Vref by 8 voltage dropped across 7 resistor and remaining voltage appeared at the point H. This voltage at point H we can get by calculation. This voltage at point H we can get by voltage division rule also. Similarly, we can calculate voltage across all points. So, voltage between point G and ground is 2 Vref by 8, between point F and ground is 3 Vref by 8, between point E and ground is 4 Vref by 8, between point D and ground is 5 Vref by 8, between point C and ground is 6 Vref by 8, and between point B and ground is 7 Vref by 8 as shown in the table. Different points are connected minus input of different comparators, and positive input of all comparators are connected to analog input voltage V in. Now, suppose analog input voltage V in is less than V reference by 8, means positive terminal input of all comparator is less than their negative terminal input. Then in such a case, output of all comparator will be 0 and priority encoder will generate an output 0 0 0. Observe it from the table. Now, suppose analog input V in is greater than Vref by 8, but less than twice of Vref by 8, then output G of last comparator is 1, but all the remaining comparator output will remain 0. Then priority encoder will give output 0 0 1. Similarly, if V in is greater than twice of Vref by 8, but less than thrice of Vref by 8, then comparator output F and G will be high and remaining output will remain low. So, priority encoder will give output 0 1 0. Similarly, if V in is greater than 3 Vref by 8, but less than 4 Vref by 8, then only output E F G will be high and priority encoder will give output 0 1 1. When comparator output D, E, F, G are high, priority encoder will give output 1 0 0. Similarly, by giving proper analog input, we can get different codes, binary codes at the output from 0 0 0 to 1 1 1. In this way, using a resistive network, we can generate all reference voltage, and using different comparators, we can compare input voltage parallelly with their reference voltages, and based on the output, we can encode it to generate binary voltage. So, this conversion is fast because all bits are compared simultaneously and the delay in the output is only due to delay of comparators and priority encoders. But here the problem is, suppose we want to design a 16-bit ADC, then for that we need more than 65,000 comparators, which is not possible practically. So, we can use flash type ADC only for small values of n. Let us look at some more practical type of ADC which can be used for larger values of n. Here we are going to discuss about counter type analog to digital converter, which is also known as digital RAM or stair step type analog to digital converter. Counter type analog to digital converter uses one voltage comparator, one binary counter, one n bit DAC, one control circuit, one AND gate and clock pulses. This ADC is more practical compared to flash type because it uses lesser number of components. Let us first understand how it is designed. Look at the schematic diagram. Here we used a counter which gets reset after every count. Output of counter is given to DAC and output of DA converter is given to negative input terminal of comparator. The positive terminal of comparator is supplied with analog input voltage. Output of comparator is fed to one terminal of AND gate and other terminal of AND gate is provided with continuous clock pulse. Output of this gate is fed to the counter. Now let us understand the working of this DAC. The counter value is initialized to 0 before starting the conversion process. Let us have a 3-bit counter. Counter output, that is 0 0 0, is fed to the input of DA converter. DA converter generates output 0. Now output of DA converter, that is 0, is fed to negative terminal of comparator and analog input is applied to the positive terminal of comparator. Input voltage is compared with 0, which means comparator output is high. So clock pulse will pass through AND gate and the counter will count 0 0 1. Now DA converter will increase output by one step and that voltage will be compared with analog input voltage. If V in is still larger, then counter will count by 1 and it will become 0 1 0. This way counter will continue counting and output of DA converter will also go on increasing and continuously comparator will compare the voltage with the input voltage. As soon as the DA converter output exceeds analog input voltage, output of DA converter will become 0. Now clock pulse cannot pass AND gate and counter will stop counting. Output of counter at that instant is our equivalent digital output. This can be seen through the characteristic. As soon as steps crosses analog input voltage, this can be seen through the characteristic. As soon as steps crossed analog input voltage, counter stopped counting. Here at the 5th clock pulse, the counter stopped counting. Now the main drawback of counter type ADC is that in worst case for n bit conversion, counter has to count 2 to the power n minus 1 times. So number of clock pulses required can be as large as 2 to the power n minus 1 and worst time required for conversion is T clock into 2 to the power n minus 1, where T clock is clock pulse time period. Say for a 16-bit ADC, we need, say for a 16-bit ADC, the counter need to count more than 65 times. That is why it has been said that flash type counter is fastest, since the whole conversion process takes place in just one step. Also, there is another issue with counter type ADC, that after each count, counter gets reset, which makes conversion process slow. Look at the diagram. If we consider input sampled voltage is equal to 4, then counter will count from 0 to 4, that is 4 times counter will count. And if the next input sample is equal to 5, then again the counter will count from 0 to 5. So this makes the process slow To overcome this problem, tracking type ADC, which is also known as up down counter type ADC, is used. Now let us understand a method which is known as tracking type ADC. This ADC is also known as up down counter type ADC. Look, we want to overcome the problem of counter type ADC, where after every sample count, counter gets reset to 0, which makes the process slow. Means we want to continuously track the input voltage. We do not want to start counting from 0 every time for every sample. So modified schematic will look like this. Here, instead of using normal counter, we use up down counter. Rest design will remain same. Here the comparator output can be 0 or 1. For V input greater than DAC output, comparator output is 1, and so AND gate output will also be 1. And for V input less than DAC, comparator output will be 0, and also AND gate output will be 0. Now here, when 0 is fed to counter, it performs down count to reduce DAC output, and when 1 is fed to counter, it will perform up count to increase DAC supply. So here we are trying to track DAC output continuously. That is why this DAC is also known as tracking type ADC. So this type of ADC is known as tracking type ADC. Let us understand with an example. Look at the diagram. Suppose input voltage is changing linearly in straight line. Here at 5th clock pulse, DAC output crossed input voltage. So here occurs one conversion. After this, DAC output is higher than the input voltage. So comparator output becomes low and down count is performed. In the next step, that is 6th clock pulse, input voltage is higher, so up count is performed. In 7th pulse, again up count is performed. So here we find that it is continuously trying to track the input. It is not starting from 0 after each count. So tracking type AD converter works much faster compared to counter type AD converter. But tracking type converter works well for signals which are changing relatively slowly, because it may not be able to track the fast changing signal. Also, in worst case, conversion time is still T clock into 2 to the power n minus 1, which is same as counter type ADC. So let us have a look on some review question related to this lecture. For a 6-bit ADC with full scale voltage of 0 to 5 volt, resolution is approximately equal to blank millivolt. So for an ADC, we have seen that resolution is equal to FSR by 2 to the power n. Here FSR is 5 volt and n is 6 bit. So putting the values 5 by 2 to the power 6 will give 0.078, means 78 millivolt. Correct answer is C. Now next question is, for a 10-bit digital ramp ADC using 500 kilohertz clock, worst case conversion time is. So to calculate worst case conversion time, the formula is T clock into 2 to the power n minus 1. T clock here is 1 by 500 kilohertz and n is here is 10. So putting the values, we will get 2046 microsecond. So the correct option is A. Look, here we have given frequency which is 500 kilohertz and we need time period. So we get it by reversing the frequency, taking the reciprocal of frequency. Third question is resolution of an ideal ADC. So here we are talking about ideal ADC. So we have seen that resolution of an ideal ADC is equal to infinite. Next question is perfect reconstruction from an infinite sequence of sample is possible when. So, here we have 4 options and this statement is from Nyquist theorem. So, it is saying that we can perfectly reconstruct our signal for which condition. So, the correct option is B, which is saying sampling rate is greater than twice the bandwidth of the signal. Next question is ADC with fastest conversion rate is. So, till now we have not seen all the ADCs, but still I want to let you know that among all ADCs, the ADC with fastest conversion rate is our flash type ADC. So, here correct option is D. Next question is sample and hold circuit is blank circuit. So, it is an interesting question, many people get confused. So, I want to let you know that a sample and hold circuit is an analog device circuit. And the last question here is mark the incorrect statement. Here are 4 statements. First one is when Fs is less than twice of F maximum, then aliasing error may occur. So, it is a correct statement. Fs should be greater than twice of F maximum. Second statement is flash type ADC is also known as digital ramp type ADC. This option is incorrect because digital ramp type ADC is actually counter type ADC. Third statement here is flash type ADC uses too much hardware. This is a correct option, correct statement. And last statement is worst case conversion time for counter type ADC is 2 to the power n minus 1 into t clock. This statement is also correct. So, here incorrect statement is option B. So, in this lecture we discussed about resolution of ADC, design of flash type ADC, counter type ADC and tracking type ADC, their advantages and disadvantages. In next lecture we shall discuss design of other kinds of ADC. With this I would like to wind up this lecture. Happy learning.